In our previous lecture, we have studied the Zbus building algorithm. That is, in that algorithm, we have studied various type of modification of a given network, because of which there will be some change in the bus impedance matrix. And we know how to determine that change. Based on those modification, we can start from scratch and build a complete network and can find out the bus impedance matrix for that network. Now let us see that through a numerical example. Here, in this example, what we are given a network with bus number 1, 2, 3, and this is the reference bus. There are 5 elements. Element A is equal to 0.25, element B is equal to 0.1 ohm, element C is equal to 0.1 ohm, element D is equal to 0.25 ohm, and element E is equal to 0.1 ohm. Now we need to determine the bus impedance matrix for the given network. Okay, now what we will do, we will start from scratch and apply our bus impedance building algorithm, and we will see how to determine the total bus impedance matrix for this given network. So for the step 1, we will add element A. That is, what we are doing here, we are adding bus 1 with the reference bus, and this is the new bus. Okay, so it is just like adding a new bus to reference bus. The new bus is bus number 1. Now for this part, the network will be like this. This will be bus 1 and only one element will be there with the reference bus, and this element is 0.25. Okay, so the voltage, let us say the current entering into the transmit network is I1. So voltage here is V1. Now we already know that V1 is equal to I1 into this impedance into Z1, or I1 into 0.25. So for this simple case, this is the type 1 modification. So only one element will be there in the bus impedance matrix. So bus impedance matrix for the step 1 is nothing but this simple element, and all other elements will be 0. Like if I want to write the complete equation, V1 is equal to Zi, V is equal to Zi, that is V is equal to Z bus into I. So what I will write? I will write V1, V2, V3 is equal to the bus impedance matrix into I1, I2, I3. As of now, this network is not having V2, V3. These can be taken as 0 also, because there is no bus which is existing here. No bus existing here. No such current existing here. No such current existing here. Only the element will be 0.25. Okay, so V1 is equal to just 0.25 into I1. So this is the bus impedance matrix from the step 1. Now in the step 2, what we will do, we will try to add element number 2. Now let us see that in the next slide. Now let us add element number B. Till now our network is just, this is bus 1 and this is element number A, and this is the reference bus. Now what we will do, we will add element number B, so our network will become like this. And this will be bus number 2. So you see, when we will add element number B, what we will be doing, we will be connecting a new bus to the already existing bus of the network. That is, for the second step, what we are doing, we are connecting new bus with existing bus, which is just bus number 1. So it is type 2 modification or the case 2 which we studied in our previous lecture. Okay, now we already know from our previous lecture that because of this, the bus impedance matrix for this step will be the earlier impedance matrix 0.25. Okay, now what will happen? This element will come here, same element, and this element will also come here, and this element will be nothing but the Z branch plus the Thevenin impedance seen from the bus which is already existing, that is Z11. So it is nothing but, what is Z branch? 0.1, and what is Z11? Just 0.25. So it is 0.35. Okay, so the bus impedance matrix for the step 2 is nothing but 0.25, 0.25, 0.25, and this is the new element which is being added, 0.35. So the network equation will be just V1 V2 is equal to 0.25, 0.25, 0.25, 0.35, I1, I2. Okay, so up to this step we have determined the bus impedance matrix for this network. Okay, now in the next step what we will do, we will try to add element number C. That we will do in the next slide. Now let's see the next step. Now what we are doing here, we are adding element number C, that is we are adding or connecting a new bus number 3 to the already existing number bus 1. So it is again an example of type 2 modification. That is we are connecting here bus number 3 which is a new bus to the already existing bus number 1. So it is again a type 2 modification. So we have seen that up to step number 2, that is the up to step number 2, the bus impedance matrix was 0.25, 0.25, 0.25, 0.35. Now what will happen? When we will add this element number C, a new bus number 3 will be there. So another row corresponding to bus number 3 will also come, 0.25, 0.25. Similarly, another column corresponding to bus number 3 will come here. Now we know that the element here which is going to come here, that is Z33. Z33 will be nothing but Z branch plus the Thevenin impedance seen from the bus to which the new element is being added, that is Z11. So Z11 is nothing but 0.25. So it will be 0.1 plus 0.25, that is 0.35. And this row and this column will be same as that of the column and rows corresponding to the already existing bus to which the new element is being added. So this will be simply 0.25, 0.25, and it will be its transpose only, 0.25, 0.25. So the equation will become like this: V1, V2, V3 is equal to, let me erase this, I1, I2, I3, and let me write this matrix as Z bus coming out of step number 3. Okay, now in the next step what we will do, we will add element number D. Okay, that we will see in the next slide. Now let's see the step number 4. In this, what we will do, we will add element number D. Okay, so you see what we are doing here, we are connecting an already existing bus number 2. That is, already existing bus number 2 is being connected with the reference bus. So this is an example of type 3 modification. So you see what we are going to do, we are going to write the equation same as type 2 modification, and then we will eliminate the last row and the column corresponding to the new bus. That is what we are going to do. We are going to introduce a new bus, let us say bus number P, and then we are going to connect this bus to the reference bus. Okay, so by connecting the new bus, that is, now what it will become, it will become an example of case or type 2 modification. That is, we are connecting new bus to the already existing bus number 2. So let us see what will happen. Z bus for the step 4 will become like this: bus number 1, bus number 2, bus number 3, and this will be the row corresponding to the bus number P. Similarly, there will be columns for bus number 1, bus number 2, bus number 3, and bus number P. So up to this point, this matrix will come 0.25, 0.25, 0.25, 0.25, 0.35, 0.25, 0.25, 0.25, 0.35. Now, corresponding to this row and this column, what we need to do, we need to write this element first, that is the element number Z44 or ZPP, or what it will be? It will be simply the Z branch plus the Thevenin impedance seen from the bus number 2, because it is being added to the already existing bus number 2, Z22, which is simply 0.25 plus what is Z22? Z22 is this 0.35, that is 0.60. So this element will come out to be 0.6. Okay. Now this row will be nothing but same as this row. And this column will be its transpose. So here we have got a bus impedance matrix which is of 4 by 4 order. Now what I will do, I will connect this bus number P to the reference bus. So when this bus P is connected to the reference bus, its voltage will become 0. So this row and this column can be eliminated because it will be having the LHS as equal to 0, because VP is equal to 0. So I will eliminate this row and this column. Now you know that for eliminating any row and column which is of the highest order, what we do, we simply use this formula: ZHI new is equal to ZHI old minus ZH and the highest order row or column into Z highest order row and the I divided by the element in the highest order row and column. Okay, where n is up to the last one, and this is the highest order row and highest order column. In my previous lecture, by mistake, I have written this as new. Please correct it to the old. It is old only. So you see that here this h and I going to vary from 1 to 3. That is up to the value n is equal to 3 here. Okay. So what I will do, I will try to solve just one element. That is like I want to find Z21 new. So what I will do, Z21 old minus Z2P, n plus 1 is here P or 4 into ZP1 divided by ZPP. That is Z21 new is equal to Z21 old. Z21 old is simply 0.25 minus Z2P. Z2P is 0.35 into ZP1. ZP1 is 0.25 divided by ZPP. ZPP is 0.6. So using calculator, it will come out to be, let me use the calculator now. Now I have taken the calculator. Let me calculate the values. 0.25 minus 0.35 into 0.25 divided by 0.6. It will give me 0.1042. So element number 21. What is element number 21? It is 0.25. Although I have taken Z12 also, but since it is a bilateral network, so our value did not change even if I used the value of 12. Okay. So you see Z21 new is equal to Z12 new, that is this element as well as this element will change to 0.1042. 0.1042. So you see, to find all the elements we have to just do half the number of the calculations because it is a bilateral network. So one of the element will be equal to the corresponding other transpose element. Now in the next slide, what I will do, I will write the complete new matrix using this formula only by just calculating one by one all these values. I have calculated these values directly, so I will write this bus impedance matrix directly. Okay, that we will see in the next slide. I have written the bus impedance matrix which we will derive from the previous step here. That is Z bus number 4. That is the bus impedance matrix which is coming out of the step number 4. Now what we will do, we will add the element number E. What it is doing? It is just connecting the already existing bus number 3 to the already existing bus number 2. So it is an example of type 4 modification. That is, in 5th number step, we are connecting bus 2 and bus 3. Both of these buses are already existing in the network. So it is a type 4 or the case 4 modification. Now, you know that for such kind of modification, the bus impedance matrix will be modified. First, what we will do, we will write the impedance matrix which is derived from the step number 4. This is row 1, row 2, row 3, column 1, column 2 and column 3. Okay. I will write it here 0.1458, 0.1042, 0.1458, 0.1042, 0.1458, 0.1042, 0.1458, 0.1042, 0.2458. Now you see that in the type 4 modification, what we do, we add a new row and a new column. Okay, that is, the elements of this new row and new column are like that, like Z, the higher order number bus to which we are referring to. Here it will be Z K. Sorry, I will write it again. These elements are nothing but Z J1 minus Z K1. What it is? Sorry, where J is the lower ordered bus to which the new branch is being added, and K is the higher order bus to which the new branch is being added. So K is equal to 3 here. Similarly, this will be Z1J minus Z1K. Okay. Similarly, this will come out to be ZJ2 minus ZK2, and it will be Z2J minus Z2K, and this element will be ZJ3 minus ZK3, and it will be Z3J minus Z3K. Okay, and this element will be ZPP or Zn plus 1 n plus 1. P is nothing but n plus 1. N is just 3 here because we are adding one row and one column. Up to here n is equal to 3, and it is the n plus 1th row and it is the n plus 1th column. These both are equal to Z branch plus ZJJ plus ZKK minus 2ZJK, where J is 2 and K is 3. So ZB is 0.1 and ZJJ, Z22, Z22 is 0.1458 and ZKK means Z33 is 0.2458 and Z23 is 0.1042, twice of 0.1042. Now let me use the calculator to calculate this value. I have taken the calculator and I will calculate this value as 0.1 plus 0.1458 plus 0.2458 minus twice of 0.1042. It comes out to be 0.2832. 0.2832. Okay. Similarly, ZJ1 is nothing but Z21 minus ZK1 is equal to Z31. It is equal to 21 is 0.1042 and 31 is 0.1458. It comes out to be 0.1042 minus 0.1458 minus of 0.0416. Okay, so this element will be 0.0416. Similarly, minus of this element will be, because it is a bilateral network, I don't need to calculate it again, it will be 0.0416. Okay, now this ZJ2 minus ZK2, Z22 minus Z32 is equal to, what is Z22? Z22 is nothing but 0.1458, and what is Z32? It is 0.1042. It comes out to be 0.0416. So this element will be 0.0416. Similarly, due to bilateral network, it is 0.0416. Okay, now zj3 minus zk3, zj3 is z23 minus z33 is equal to, what is z23? It is 0.1042 minus what is z33? It is 0.2458. It comes out to be 0.1042 minus 0.2458, that is minus of 0.1416. so this element will be 0.1 minus of 1416. Similarly, this element will be minus of 0.1416, and this element I already calculated it as 0.2832. Now I have got one 4x4 matrix here. This is a 4x4 matrix and I need to eliminate this row and this column. Now, in the previous step, I had shown how to eliminate one by one. Okay. Now, instead of doing that, instead of using that formula, I will show you how to utilize the matrix partitioning method. Okay. In our one of the previous lectures, we have studied how to eliminate any row or column using matrix partitioning. I will partition this matrix here like this, and it is like this. So this matrix, this 3x3 matrix is nothing but K, and this matrix will be L, and this matrix will be L transpose, and this single element matrix, let us say it is M. Okay, now we know that K new is nothing but K old minus L M inverse L transpose. Okay, so K new is nothing but K old 0.1458, 0.1042, 0.1458, 0.1042, 0.1458, 0.1042, 0.1458, 0.1042, 0.2458 minus what M inverse will be simply the reciprocal of this element, because it is a single element matrix. For a single element matrix, inverse is just the reciprocal. So I will write it first here because it is just a single element. It will be 0.2832. And what is L? L is a 1/3 matrix. And what is L transpose? It will be a 3/1 matrix. Okay. So instead of writing it here, I will just erase this and write again, so that the space is not insufficient there. That I will do in the next slide. Now in this slide, I have directly written all the values. It is the K old minus M inverse L into L transpose. L was simply minus 0.0416. 0.0416 minus 0.1416, and L transpose is simply written here. So using just the matrix part of the scientific calculator, I can write K new is equal to the required bus impedance matrix for the given network, because all the elements have been added now. So the required bus impedance matrix is simply this, which I have written here. Okay. Now to show you one of the concept that what happens to the bus impedance matrix when we remove one of the lines. Let us say I want to remove this line. Okay. Now if I want to remove this line, so it is simply equivalent to adding a line in its parallel which is having impedance equal and opposite to the line which is being removed. So this line, let us say it is element number F, will be added having an impedance minus of 0.1. Okay, so up to this point this network was having this impedance matrix. Okay, so you see that adding of this element number F is nothing but adding an element between bus number 2 and bus number 3. So it is again a case of type 4 modification. Okay, so type 4 modification requires that I write Zbus for this element. Let us say I write it as step number 6 is equal to Zbus old minus M inverse. Now for this step, M will be Z branch plus ZJJ. J is simply 2. Again here J is 2 and K is 3. Okay, it is similar to the step number 5. So Z22 plus Z33 minus twice of Z23. So in this matrix I will find all the values. This is Z22, this is Z33 and this is Z23. So ZB is minus 0.1 plus Z22 is 0.1397 and Z33 is 0.1750 minus twice of Z23 0.1250. So using the calculator I will write this value here. Now I have taken the calculator. Minus 0.1 plus 0.1397 plus 0.175 minus twice of 0.125. It comes out to be negative and it is minus of 0.0353. Okay, so M inverse will be simply reciprocal of this. Now I have to write matrix L and L transpose. Now you know that matrix L and L transpose are composed of elements which are simply ZJ1 minus ZK1, ZJ2 minus ZK2, ZJ3 minus ZK3. That is Z21 minus Z31, Z22 minus Z32, Z23 minus Z33. So it is nothing but subtracting this row from this row. So I will write the element of matrix L here directly. What it will be? 0.1103 minus 0.1250 minus of 0.0147, 0.1397 minus of 0.1250, 0.0147, 0.1250 minus 0.1750, 0.05 minus of 0.05. Okay, now L transpose will be simply its transpose minus 0.0147, 0.0147 minus of 0.05. Now I can get the bus impedance matrix using this equation where Zbus old is this bus impedance matrix. Okay, now what I will do, I will solve this equation directly using my calculator and I will write all the values of Zbus 6 using this equation here in the next slide. Now I have written the bus impedance matrix from the step number 6, that is by adding this element which is having value equal and opposite to the existing line, that is it is equivalent to removing this element altogether. Now we find that this bus impedance matrix is equal to the impedance matrix which we have seen in the step number 4. These two impedance matrices are equal. So you see that removing a line is equivalent to just adding a line which is having an impedance equal and opposite to that of line. So in this way we have shown how to utilize the bus impedance algorithm to find the bus impedance for the complete network. And one more concept was shown, that removal of a line is just equivalent to adding of a line having an equal and opposite impedance. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.